Welcome to a new video. In this video we will discuss the Gaussian elimination. Gaussian elimination is used to calculate the unknowns in a set of equations. We will see that shortly, that we can put that in a matrix and work it out such that we have the unknowns we want. Of course, we will see that step by step in our calculations and also show you how you can do that also in MATLAB. Okay, now we have the following objective. We would like to solve the following system of equations. So this is a set of equations using Gaussian elimination. Now this is the set of equations. You see here 3 equations and there are also now 3 unknowns. So we have x, y and z. So how do we solve now the x, y and z in this set? Okay, now let's look at the solutions. The first step is, in our calculations, put this form in a standard format. What is the standard format? Now in this case you see here x, y and z and there is a number. But the second one is not in the standard format. It starts with an x and then y, but then is equal to the third unknown. So we need to have everything in the same order. So that's actually shown here. So you see here the first equation is as it is. But from the second equation I moved that z from the right side to the left side, so it will be minus z is equal to 0. So I need to have at the right side, after the equation equal signs, all constants. Okay, the third one is also not in the standard form, so I need to move this 6y to the left side, so it will be minus 6y, but I also need to move this 1 to the right side, it will be minus 1. So you have actually here minus 6y from the right side, and then also 1 goes to the right side, will be minus 1. Now everything is in the same order. You see here x, y, z a number, x, y, z is a number, x, y and z is a number. So now we can put this in a matrix form. So that is the second step. So augmented matrix means there's a matrix which is augmented with a vector, which is the vector what we see here. So that is now the format. You see here that we only put the coefficients from the unknown. So we put here the 4 here, the minus 2 here, and the 1 here. So that is here, that's the first row, and that is equal to 2, but that equal sign is not visible here, that's just actually here a vertical line. Now similar form for a second row, see here 2 and a 1, and a minus 1 is equal to 0, so there's actually 0 here. Now in a similar form the third one, 1, minus 6, 5, and there is a minus 1 there. So how do we solve now this one? Now we need to know what the x, y and z is. That is our final goal. Now the Gaussian elimination tries to make this 3 values here or numbers 0. So how do we do that? And there is a procedure for that. So in order to do that we try to eliminate the 3 values here by making operations like the row 1, a row 2 and row 3, subtracting or adding that together. Let me show you that in the first round, what we need to do in order to do that easily. First I will double the second row. Why? Because I would like to have also a 4 here. You will see why that is handy. I will also make this third row 4 times. So that this is the meaning of 2 times R2 meaning row 2, and this is 4 times R3. So that means R1 is not changed, so everything's actually staying here the same. The change is only in the R2 and R3. So you see actually here 4, minus 2, 1 and 2, that's actually just a copy. But here everything is doubled. 2 times this, 2 times that one, 2 times that one, 2 times 0 is 0. And here everything is times 4. So that's 4. This is minus 6 times 4, so minus 24. 5 times 4. And this is minus 1 times 4. Now why is this handy? Now you can see that I can now make the operation like R3 minus R1 and also R2 minus R1. Then I can remove this, so I can make this 0. So the order is make this 0, and then finally this 0. So you actually make a triangle of zeros. So that's the next steps. So we have here R3, so row 3 minus the row 1. That means row 1 is still not changing, but only changes here the row 3. We also do right away row 2 minus row 1, so it means row 2 is also changing. Okay, now we have the following situation. Again, we always start with the part which is not changing, which is on the first row. So take it over, just copy that. Let's see first row 2, what happens. Now you do here 4 minus 4, because that's actually what it says here. And then 2 minus 2, that will be a 4. So 1 by 1, minus 2, minus 1, that's actually minus 3. And then 0 minus 2 will be minus 2. Okay, that's for row 2. Row 3, we also need to do that. So row 3 minus row 1. So again, from here, minus this one. So 4 minus 4 will be 0. So again, as we wanted, so this was the objective. That was also the reason why we doubled that and also make it 4 times. Okay, minus 24 minus 2 will be then minus 22. So you need to add 2 actually effectively. And here, 20 minus 1 will be 19, and we have here minus 4 minus 2 will be minus 6. Okay, now we are almost there. We only need to make this 0. So how can we do that? Actually, in the symbol form as we have done that in the first step. So we need to create here a value which is exactly the same as this one, or in a different sign. It doesn't matter, but something with a 22. Okay, now we can say this 4 needs to multiply by 5.5 in order to get this 22. So that means row 2 needs to multiply by 5.5, and everything stays the same. The rest is exactly as it is. So we just copy row 1 and row 3, but this is now changed by multiplying it by 5.5, each number here. So you see here, this is not changed, so just a copy. This one is exactly a copy. Here, 0 times 5.5 is 0. 4 times 5.5 is exactly 22, so that's actually why we did it. And we have here minus 3 times 5.5 will be minus 16.5. And we have here minus 2 times 5.5 will be minus 11. Now, we are very close to what we want, because now we see here that row 3 and row 2 can be added together in order to get this 0. So let's take this here, copy that, and then move on here with the operation we want. So row 3 plus row 2. So again, if you say row 3 plus row 2, that means in this calculation that the row 3 is changing. And that means row 1 and row 2 is not changing, so you can just copy them first. So you see here, this is not changing, this is not changing, but this has changed. Why? Because we have here minus 22 plus 22, that's 0. 19 plus minus 16.5 will be 2.5. And then minus 6 plus minus 11 will be minus 17. So that is exactly what we wanted as our form in a final augmented matrix, but we need a triangle of zeros here. So now we can do the calculation easily to calculate the x, y, and z here. Now the step 3 is now solve now the unknowns one by one. Now then we have following. You can look at this row here. What you see is actually 0 times x plus 0 times y, because what we have here is just the coefficient of x, the coefficient of y here, and here we have the coefficient of z, and that is equal to minus 17. So that means 2.5 times z is minus 17. So that's exactly the reason why we need to have here only one unknown. So that's the reason why we need here 2 zeros. So if you calculate now this, pretty straightforward, you say just z is equal to minus 17 over 2.5, and that will result in minus 6.8. Now we have this. Now we can back substitute that in the second row, because this part is now known, because that is minus 16.5 times this minus 6.8, and we can calculate now the y. So in the second row, we can now say, hey, there's 22y, because this 0 is 0 times x, so it is disappearing. So 22y minus 16.5z is equal to minus 11. So how do we calculate now the y? Now we can just put this to the right side. So this minus 16.5z goes to the right side. And you divide everything by 22. Now we know what z is, just calculate it. So just substitute that here. And that will result in minus 5.6. So you see actually here, we go from the bottom to top and then back substitute, and we calculate our unknowns one by one. Now we develop here the equation for the first row. So we have to see here 4 times x minus 2 times y plus z is equal to 0. Now we have here everything except x, so we can again express the x in terms of the other parameters. So let's first isolate x. So 4x is equal to, now this one goes to the right side, this one goes to the right side, so we see here this will be 2y, this will be minus z. Again, now divide everything by 4, you see that here. And now we can substitute the y, which is determined here, and z, which is determined here, so we have it here. And that will result in minus 0.6. Now we have all the unknowns for this set of equations. Okay, now the summary is, these are the results, x, y, and z. Let's check our results by substituting these values in this set of equations. Now let's do that 4 times the x and then minus 2 times y plus z. So from here, you can see that here that it will result indeed in 2, so that means this is correct. And the second one will result in 0, just substitute the x, y, and z, and the third one is producing minus 1. So this is all correct, so we can say our results are indeed correct. Now let's see that also in MATLAB. So this is again our summary. These are the results for the x, y, and z. And in MATLAB you can produce that matrix, what we have here. This is the matrix, I call this A, by using this command in the command window. So you can here create a matrix with 4, minus 2, 1, 2, 1, minus 1. You see that actually here, this is the matrix, and then you see also here 1, minus 6, and 5. So this one, this part only is shown here. And the B is the vector, which is then this is 2, 0, minus 1. You could do that actually by this. You see a semicolon, semicolon to make it vertical. Now you have now matrix A and a vector B. So this is matrix A, this is vector B, and then you say V is equal to, you can also call it here P if you want, or Q, doesn't matter. Lin solve, and then parentheses open, and then you do A, comma B, and parentheses closed, and you see here the results. And the result here is in order x, y, and z. Of course, the MATLAB doesn't know that you have an x, y, z. It could be also A, B, C, or x1, x2, and x3. It doesn't matter. But the first one, and the second one, and the third one, those are in order as you have chosen, and that's actually also what we have here. That's all as we have calculated. So again, we define a matrix, we define a vector, and we solve it using this operation in MATLAB. And we see that this is indeed as calculated. Well, right, this was our example considering the Gaussian elimination for this system of equations. This is, by the way, also called a 3 by 3 matrix, because we see here 3 by 3, so 3 rows, 3 columns. If you have any questions, comments about this example, please let me know. I will try to answer them as soon as possible. See you next time in another video.